Hi everybody. Here's our next lecture. We already started this in the last lecture, the PowerPoint part of Chapter 17, which is kind of conceptual stuff, nomenclature, structure and properties of ketones and aldehydes, and a little bit of NMR spectroscopy. All right. So we already started this. I'm not going to show this again, but we talked about the nomenclature, basic nomenclature of aldehydes and ketones. I should say that you haven't been quizzed much on these, really at all. Most likely on the final super quiz, the final exam, I'm probably going to have a question or two. So don't completely ignore this stuff. And when you study for that thing, you should probably review these conceptual details a little bit. Okay, so we talked about the naming of ketones and aldehydes, blah blah blah, and then we did a couple of the common names that you see all the time. All right, and then this is where we got. So, just so you know, there's a lot of examples of more probably ketones in pharmaceuticals than aldehydes. And the reason is because ketones are more stable. Aldehydes are a little less stable. They're a little more reactive. And so we don't really see aldehydes in drugs. I'm trying to think. I don't have any off the top of my head. There are probably a couple. But for the most part, ketones, if you think about pharmaceuticals, are present in more drugs. A couple that stand out, I think, are Oxycodone, which is a opioid analgesic, so it's one of the painkillers. It's used in, abused a lot actually, and there's a lot of ongoing lawsuits about this. Oxycodone in a time-release formula is called Oxycontin. It's the same drug. These are both agonists of the opioid receptor, the mu opioid receptor, and they cause sort of the pain-killing effects that are associated with opioids. There's a bunch of opioids. They all have kind of related structures. For example, codeine and morphine kind of look a little different. They have the alkene down here, and rather than the ketone, they have the hydroxy group. I want to say that morphine might have an OH up top, or there's some difference in the structure of the ether. Might be an alcohol for morphine. Okay, so then there's also other, while we're talking about ketones, there's opioid antagonists that kind of prevent the activity of opioids, and they're actually used in sort of abuse management of opioids. Naloxone is one of these. I think naltrexone is one of the other ones, but they all kind of look kind of similar, but they bind to the opioid receptor in a way that prevents activity rather than causes activity. Just another example of a ketone. There's a bunch of ketones in drugs, but tetracycline has a ketone functional group, and it's an antibiotic, and there's other things, kind of, all sorts of classes of drugs that have ketones in them. The structure of carbonyls, so C double bond O things, ketones and aldehydes, for example, are, they're short, and it's highly polar, meaning there's a lot of reactivity, and that's why it's fun in organic too, because we talk about all the reactivity of ketones and aldehydes. Hybridization is both sp2, because there's a double bond, right? So that's the double bond in the middle. The pi bond is filled with p orbitals. So we have basically p orbital on carbon and p orbital on oxygen, and that's how we form the pi bond, which is the second bond. This just shows some of the geometry. The double bond O is relatively short because you have two bonds relative to other bond lengths. A CH bond is actually kind of short also, but like a CC bond is kind of a little bit longer. And overall, the bond angles are roughly 120 degrees because it's sp2. big thing for organic 2 is that the carbonyl is electrophilic, meaning it can be attacked by nucleophiles. Okay, and the reason is oxygen is more electronegative than carbon. So you can see that, of course, that the oxygen, there's resonance between the C double bond O and like a C plus O minus thing. You can almost say that the carbon's semi-carbocation like. So nucleophiles will attack it, right? We know that already. You've learned this before. Grignards, right? Grignards attack ketones and aldehydes, right? We learned that. So that's an example of a ketone or aldehyde being electrophilic. We also sometimes draw this with a little arrow, and this just shows electron localization on the oxygen. Okay. Formaldehyde, this is one of those electron density graphs. And the red is sort of electron density. The blue is electron deficiency. You can see the carbon is kind of electron deficient and explains its reactivity. Another interesting thing is that aldehydes are more electrophilic, more likely to be reactive. Ketones are less electrophilic. And that sort of explains what I was talking about with pharmaceuticals. So aldehydes are kind of reactive, and you wouldn't really want a reactive substance as a drug usually. And in most pharmaceuticals, you want stability, and the ketone provides stability. Okay, so there's two reasons for this. One is sterics. If you imagine a nucleophile and it's attacking an aldehyde, well, there's one thing that's bumping in the way. Whereas if it attacks a ketone, there's two things bumping in the way. So that's an easy rationale for why a aldehyde is more reactive and ketone is less reactive. The other reason is hyperconjugation, which this we've talked about in kind of like carbocation stability. Do you remember that? Carbocation stability, organic 1, of like why a tertiary carbocation is more stable than a secondary carbocation, and So it's the same kind of idea that the things on the carbonyl, whether it's an aldehyde or a ketone, can sort of donate their electron density in to stabilize the positive charge a little bit. Okay? It's an electronic effect. And aldehydes have that, and ketones have it. But aldehydes have less of it because they only have one alkyl group on the aldehyde. So there's less hyperconjugation and less stability, and that makes it more electrophilic, more reactive. When you think about hyperconjugation, you also think about the CHs. The CHs that are on the neighboring carbon, those have electron density, and those will kind of stabilize the partially positive charge on the carbon. So aldehydes have less of it. Ketones have more of it. They have more hyperconjugation, which causes more stability. When things are more stable, they're less electrophilic in this example. All right? So two reasons, sterics and hyperconjugation. And hyperconjugation is an electronic effect. Aldehydes, NMR. Let's talk about NMR a bit. You know this. This was actually our first example of complex splitting. Remember the doublets of triplets and all that kind of stuff we learned about in NMR? First we learned about aldehydes. Then we learned about alkynes. And now we're back to the aldehyde chapter, so now we're going to talk about aldehydes again, okay? Aldehydes couple to neighboring CH groups with smaller coupling constants than usual, okay? And that causes complex splitting. So here's an example. Acetaldehyde. This is a simple molecule. We'll do a little more complicated in a second. First thing about an aldehyde is that the aldehyde CH comes downfield, right? Remember that? It's beyond a benzene. It's like super downfield, 9 or 10 ppm. So that's where they come. And where do the protons next door to an aldehyde come? So this is all on your chart, the NMR chart. Aldehydes come at 9 to 10. If you're next door to an aldehyde, you are next to a pi bond, right? Because that is a pi bond, and next to pi bond we said was 2 to 3 ppm. So perfect. Everything lines up. The other thing, though, is the splitting has a small J value, 3 Hertz. So this is a quartet because the CH sees the CH3 quartet. And this is a doublet because the CH3 sees a CH next door. But the big thing is the J values are small. Because what's a normal J value? We say 7 to 8. 7 to 8 for a normal J value. All right. And different coupling constants can lead to what phenomenon? And that is the complex splitting thing that we saw in alkynes, for example. All right, so this CH2 is nothing special about it. The only thing maybe special is it's next to a OCH3. So the chemical shift will be what? That's next to an oxygen, electronegative, so kind of 3 to 4-ish, 3.3 ppm. It's a triplet, and it has a normal J value because it doesn't see that aldehyde that's in the distance. So triplet, J equals 7. This, first of all, where does it come? Well, probably in that 9 to 10 region where aldehydes come, right? What is it going to be? A doublet, triplet, quartet? Well, how many neighboring protons are there? There's 2. So it should be a 2 plus 1 is 3. It should be a triplet. But it can be a big J value or small J value. Looking at like the top as a guide, you'll say, oh yeah, it's probably small. And you're right. So 9 to 10-ish, triplet, J equals 3. All right, everything's cool, right? So now this one is the weird one because it sees a doublet next door with a small J value because it's 3 Hertz, and it sees a triplet on the other side, because there's 2 protons, with a big J value. So what do we get? A doublet of triplets. J equals 3 and 7. So that's, this is very similar to what we saw before, like for alkynes. Difference with alkynes, though, is alkynes are long distance. This is not long distance. These are like next door, right? It's a CH directly connected to a CH2, but the aldehyde does something to the J value that makes it small. I don't know the physics of that. Okay, and then lastly, what about this guy? The really boring one. Where does it come, roughly? Well, it's a CH3, but it's next to an oxygen, so kind of like 3.2 or 3 to 4, basically, and it's a singlet. All right, cool. This shows that this is a NMR simulation of that molecule. And yeah, I mean, you see the peak way down, 8 or 9. It's a small triplet. Then we see a normal triplet, a big singlet, and the doublet of triplets, right? And I'm giving them letters A, B, C, and D. I'm going to let you do that assignment. You should be able to do it. It's not that hard. Okay? So assign A through D. And that helps. And where is the doublet? If you have an aldehyde and you have this small J value stuff, and you have a doublet of triplets, for example, where would that always be? A complex multiplet? Will it be? It can't be the aldehyde proton because that's probably down at 8. It's always going to be where? It's always going to be right next door. Right, because it sees the aldehyde and it sees like a CH2. All right. Ketones are not directly observed by proton NMR, but their presence can be implied. How did we, if you remember our very, very first problem first NMR problem we did, it was like a ketone with methyl on one side, isopropyl on the other, right? And we figured out there was a ketone. Do you remember how we figured it out? You'd have to look back at the NMR chapter. We talked about we showed these examples. The first one we actually solved, we figured out it was a ketone. And we figured out, oh, it's a mystery functional group, right? So how did we figure it out? There were 2 things. One was degrees of unsaturation, UN, right? UN equals 1 at least for a ketone. And the other thing is we had an extra C and an extra O that were unassigned, right? You have to go look at that problem. It was really fun. Chapter 13, the last part of chapter 13, we were doing a bunch of problems. But that's how we figured it out, is UN equals 1, and we had a mystery C and a mystery O. Check out that problem again. Okay, and the other thing is that the alpha CH, or CH2, is always 2 to 3 ppm because it's next to a pi bond. The same with aldehydes. The location is always 2 to 3 ppm. These are just some miscellaneous ketones. Acetone, methyl ethyl ketone. This was the one we did in this one. Third one was the one we did in that really fun NMR problem. And we figured out we had a ketone by our systematic process, right? But anyway, all the neighboring CHs are roughly 2 to 3 next door to the ketone. They are also clearly identified by carbon NMR. We don't emphasize carbon much in this course because proton gives you everything you need. But if you ever do research with NMR, you'll definitely do a lot of carbon NMR. This just shows some of the carbon NMRs, and like, look at those ketones. They're really downfield. 200 to 220 usually. 200 to 220. So ketone really stands out. Aldehydes also stand out in the same region. Okay? More so than like an ester or a carboxylic acid. Those are at 180 or so. So ketones and aldehydes really stick out far downfield in the carbon. This just shows an example of a carbon NMR of a ketone, and you see 214, that's the ketone, a couple aromatic CHs. These is symmetric, so there's like 2 CHs and 2 CHs. Those are the big peak. The little peak is the quaternary carbons, and then this is the CH2 on both sides of the ketone. Okay. This is just a fun. Remember the depth. Remember depth. Again, we're not really emphasizing this, so don't worry too much about it. But it is cool. Depth was the thing that told us CHs versus CH2s versus CH3s, right? So this is camphor sulfonic acid. It's just a miscellaneous molecule. It's got a ketone in it, right? We see something way down here. There's the ketone, right? And remember depth, though? Yeah, can any of the carbons be assigned? I don't know. What do you think? Can any of the carbons be assigned? And also, are all the carbons accounted for? So when we say ask all carbons being accounted for, we count the carbons, right? And we see 1, 2, 3, 4, 5, 6, 7, 8 carbons. DMSO is a solvent, so skip that. Ignore that. We see 8. Is that how many carbons we got? Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Because the 2 methyls are actually different because one is closer to the ketone, the other is away from the ketone. So the methyls are all different. Basically, every carbon's different here. Oh, okay, well, we have a problem then because we have 8. We counted 8, but there's... Sorry, we counted 10, but there's 8 carbons that we see. Now, if you zoom in, you actually see that the left peak around 49 is actually 2 peaks. And the right peak around there is also 2 peaks. So now it actually adds up to 10. So we say 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we actually see our 10 carbons now. And then remember depth, just to emphasize this cool technique. Depth just points CHs up. Okay, and this will help in our assignment, right? CHs go up. Okay, well there's 1 CH. How many CHs are in the molecule? I don't know. How many CHs do you see? There's 1 right in the back, right? Okay, so now we know that peak is the CH, right? And then the depth 90 is CHs up. Depth 135 is the other one. CHs and CH3s up, and CH2s down, right? That was back in the carbon NMR section. That's really cool. And remember also with depth that the quaternaries, which are peaks that don't have any protons on them, disappear. So like the ketone's gone, right, in the depth. Ketone's gone in the depth. And also this peak at 60 is gone. What do you think the peak at 60 is? Any other quaternaries here? I think there's actually there should be actually 2. There's 1 there and 1 there, and the ketone. So there should be 3 peaks gone. I'm seeing 1 gone, which is the one at 60. I think there is another one, and I'm just not seeing it this second. But that because the one next to the methyls should be disappearing. It's there somewhere. Okay. Anyway, and then so CHs are up. We see a CH. There's only one CH, so now we know where the CH is, right? And then we also see 4 CH2s. 1, 2, 3, 4. Those are 1, 2, 3, 4 CH2s. We got our 4 CH2s. And then CHs are up and CH3s are up. So we see these two peaks on the right are CH3s. Okay. Anyway, that's pretty cool. 48. Yeah, I think the other quaternary, because there's two quaternaries, right? There's this one and this one. I think the other one might be buried into this peak around 45. Okay, but there's definitely two quaternaries. All right. Okay, so we are done with the PowerPoint section of Chapter 17. And we're on to the kind of reaction mechanism synthesis part. Okay, so we did 1 through 3 in PowerPoint, which was I think the nomenclature, structure, and spectroscopy of them. Okay, so now we're on to 4, which is some reactions and specifically preparation of ketones and aldehydes. Preparation of them. You know some of this stuff. This is not all new. So first we're going to talk about aldehydes. And we'll talk about a couple of the ways you can make an aldehyde. One is via oxidation. So, oxidation. This you learned in Organic 1, and the mechanism of oxidation is pretty straightforward. We'll review it just so you remember. Okay, so R, 2 carbons OH, R, 2 carbons OH, aldehyde, right? Remember that the reagent that you would use is PCC, and it's all of these oxidizing agents that we learn in organic chemistry are based on chromium for OHs. So PCC is a chromium-based reagent, and I'll review the structure of it. It's Cr, double bond O, Cl, O minus. Okay, so something negative. So what's the positive thing? Something negative has to be associated with something positive, and the positive part is pyridine, which is a benzene with a nitrogen, but it's got a proton on it, and that gives it a positive charge. Okay, so it's a salt. It's something negative, something positive. That's PCC. Name of it is pyridinium. Of course, that is pyridinium. That is pyridine. That is pyridinium. Chlorochromate. The chlorochromate part is the chlorine chromium thing. Anyway, what's the mechanism of this? I'm going to give the abbreviated mechanism because it was really an Organic 1 thing. I'm not going to test you on this mechanism because I think it's not that exciting. But anyway, oxygen attacks chromium and kicks electrons onto one of the oxygens. What does that give you? OH chromium, blah blah blah. Just a bunch of stuff on chromium, and a plus charge. Okay, I'm kind of ignoring all the details. It's just a bunch of stuff on chromium. Chlorine, O minus, right? But I'm just abbreviating that. Okay, and next thing is that some kind of base takes this proton. That's easy. Base takes proton, and you got chromium, blah 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 blah, right? And the next thing that happens is a proton takes this proton, a base, a mild base, it could be chloride even, takes off this proton, and now that's where the oxidation takes place. So the proton gets removed, now it makes the double bond O, breaks off the oxygen-chromium bond, and puts electrons on the chromium, which reduces chromium because it's got extra electrons, and that gives you the aldehyde. Okay, we did other details on this in Organic 1. I'm not going to review it. But that's one way to make aldehyde, is oxidation of a... to make an aldehyde, oxidation of a... what kind of alcohol? Is it primary, secondary, or tertiary? This is a primary alcohol, right? Yeah, okay. Also, just note, while we're talking about oxidation, that if you use a primary alcohol and you use a stronger oxidizing agent, I guess, CrO3, which is chromium trioxide, it does the same exact thing. Oxygen attacks chromium, blah blah blah. But the problem is that it makes the aldehyde, but then continues and makes the carboxylic acid. Okay, so that's a OH. Sorry, there we are. It's a carboxylic acid drawn in there. Okay. So that's a problem. If you want the aldehyde and not the carboxylic acid, then you don't want to use CrO3. Also, there's acid H2SO4, I think, or H3O+. So if you want the aldehyde, you should not use CrO3. You should use PCC to oxidize a primary alcohol. Okay. The other little tidbit is that in order for this to work, we usually use dichloromethane, DCM, as a solvent. Dichloromethane. The salt is DCM is CH2Cl2. DCM, CH2Cl2. That's the typical solvent we use for PCC. And for CrO3, the solvent is H2SO4, sulfuric acid, and that's because this actually only dissolves in sulfuric acid. This stuff will dissolve in organic solvents, and that's part of the reason that it will stop at the aldehyde. Why PCC stops at the aldehyde is because it can be done in the absence of water. Okay, DCM does not have any water in it. We will talk about that later. I think even in this chapter. All right. What other ways do we know to make aldehydes? Other ways to make aldehydes. Also, going back to Organic 1, I mean. Via ozonolysis. Ozonolysis, which is O3, right? So if we react an alkene with O3 followed by zinc and acid, we can make aldehydes. This is chapter 12 actually, CH12. We learned about this in Organic 1. And this one up top we learned in chapter 8, I think. I think it's chapter 8. Oxidation was chapter 8. Okay, so chapter 12, ozonolysis, basically just cleaves the alkene and leaves a pair of carbonyls. So it looks like in this case it made a pair of aldehydes, right? What if we had methyls on the alkene, then it make ketones, right? Because you have CH3s and it make ketones. Alright, what is the mechanism in a nutshell? Probably long forgotten, but if you took Organic 1 with me, you definitely learned this. Did we draw the alkene? Draw ozone as like O double bond O, single bond O, like that. dot, 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 dot. It kind of lines up. Any charges I'm missing? Oxygen bound to 3 things is always what charge? Oxygen bound to 3 things is always positive. Oxygen bound to 1 thing is always negative, right? So basically this just snaps on to the alkene, and I'm just going to draw a lone pair, kind of go like that. Alkene goes this way, and then just 3 arrows. And that just snaps this A plus B makes C. So it just snaps those 2 things together. And you get this intermediate that looks like oxygen, oxygen, oxygen. It says a name. It's where the ozone gets attached. We call this a primary ozonide. Okay, and the primary ozonide, and I draw a little funny arrow because the mechanism is really weird, and we're not going to do the mechanism, to make something called the secondary ozonide. The secondary ozonide is a rearranged structure which has one of the oxygens just sneaks in between the CC bond. So it's like that's kind of like, you know, the left side. But then we have an oxygen in the middle, and then 2 oxygens here. See what happened? Oxygen snuck in. There is a mechanism for this. I never talk about the mechanism because it's a little weird, and I think it's maybe controversial of how this all happens. And it's not that big of a deal. I think this is easy. I teach how ozone attaches. Okay, so then the last conversion with zinc and acid kind of breaks down the secondary ozonide and essentially gives you the 2 aldehydes. This will be kind of understandable by the end of this chapter. There's some parts of this that actually we can learn, right? This is actually doable by the end of this chapter. But this, you know, you could learn about this if you really want to. It's in the book, I think, maybe the primary to secondary ozonide. Okay, so we're still on chapter 17, of course. Number 4, preparation of ketones and aldehydes. Specifically, we're talking about aldehydes right now. And the third method we will talk about is also review. So it's funny to think you actually know a lot already from Organic 1 and Organic 2. But one of the methods to make aldehydes is from hydroboration oxidation of alkynes. So we learned this in this course, in chem335. So remember, the basic idea is that another way to make aldehydes is take an alkyne and do a special reaction. 1, 2, 3, 4. 1, 2, 3, 4. That basically turns the terminal carbon of an alkyne into an aldehyde, right? 1, 2, 3, 4. 1, 2, 3, 4. And it did, you know, the last step was something about an enol. So you make an enol, and then it tautomerizes to the keto form, which is the aldehyde functional group. And what was the reagent? It was HBOX. What does the B mean? What element is B in the periodic table? B. It's hydroboration. It's a boron thing. So it is 1 HbCy2. And all the boron reactions end with NaOH, H2O2. Okay. I'm not going to review the mechanism, aside from just mentioning in broad terms that the boron H thing just snaps on. I'll draw what you get. Just to remind you, it's BCy2H. Cool. And then there's a couple steps, a little bit of magic because of the carbon boron gets converted to a carbon oxygen from the second step there. But that's the main thing. And why does it go to the end? Why does it, which is anti-Markovnikov, right? Anti-Markovnikov. The reason it goes to the end is because of the CY. The cyclohexyls are huge, and it wants to be out in space. Okay, so very cool. That is the third way to make aldehydes. Okay, let's do ketones now. So ketones. First way is also via oxidation. And if you have oxidation of a secondary alcohol, so you need a secondary alcohol to make a ketone. Example, I don't know, there's a boring secondary alcohol with some stuff, and we want to convert it to the ketone. Alright, what is the reagent to do this oxidation? It's kind of like the one we just talked about for aldehydes. It could be PCC, DCM, dichloromethane solvent. Now if you skip the DCM, that's not a big deal, but in reality it is really important to use DCM. But we don't have to worry about over-oxidation of a secondary alcohol the way we worried about over-oxidation of an aldehyde. So we could actually get away with CrO3 acid, sulfuric acid, or whatever acid. Okay? Because over-oxidation is not a problem here, because it only can oxidize one step to the double bond O. It goes to the same kind of intermediate. I'm just going to abbreviate CR, blah, 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 whatever. And then the loss of the proton, base takes proton, so it's all the same how these chromium based oxidations work. And there's another step where the oxygen has a proton on it, but that's not a big deal. But yes, this is one of the ways to make a ketone, right? Alright, so then we can also do ozonolysis O3 of alkenes, just the same as to make an aldehyde. Let's make it really exciting and have an alkene with a couple methyl groups. Of course. Looks something like that. Alright, it cleaves the bond. And it makes a pair of ketones in this case. It's the same mechanism, I'm not going to redraw it. What are the reagents? O3, zinc acid. Okay. Same mechanism. Ozone snaps onto the alkene, makes a primary ozonide, gets converted to a secondary ozonide, and then through a little bit of magic it breaks down and makes the ketones. Okay. What about this molecule? If we do the same thing, how many products are there? How many alkenes are there? Well, there's two alkenes, they both get cleaved, so one gets cleaved there, one gets cleaved there. So one product will contain two carbons. It'll be a ketone or aldehyde. It'll be an aldehyde, two carbon, acetaldehyde, and then you'll have a ketone there, and then a ketone there. And then what about this thing? It's a one carbon thing that's going to fall off. One carbon aldehyde called formaldehyde, right? So our products here are ketone, ketone, formaldehyde, acetaldehyde, two carbon aldehyde, and then what's the third product? We have product, product, and what's the third product? It's formaldehyde. 1-carbon aldehyde. Okay? Yes, and it's the same exact mechanism, same everything. And this is an ozonolysis of a slightly more complicated alkene. We're still on the generation of alkenes. Sorry, ketones. Another way is from the Friedel-Crafts reaction. Last chapter, or Friedel-Crafts reaction, acetylation reaction, where, remember this? Acid chloride, AlCl3. Well, that makes ketones, right? And this is an EAS reaction. I'm not going to review it. You can review it. It's in chapter 15, right? It's chapter 15. The basic idea of the mechanism was that the chloride talks to the aluminum and forms a coordination, and then this aluminum tears off the chlorine and you make a carbocation, and then the benzene attacks it. EAS, electrophilic aromatic substitution. EAS. Okay. D. Via oxymercuration, demercuration of alkynes. Oxymercuration, demercuration. So this is another alkyne reaction we learned. This is the Markovnikov one. The anti-Markovnikov one was the boron one, hydroboration, oxidation, which we talked about in the aldehydes. We were making aldehydes, right? So yeah, we can make alkynes this way. Let's just imagine I don't know, random alkyne, and we do our oxymercuration, demercuration, and we get a ketone. And it's Markovnikov. We'll review the reagents, but the last step of the mechanism, and this was talked about in the alkyne chapter, was also a enol ketotautomerism. So you may have the enol, and then it goes to the keto. And what is the reagent for the oxymercuration, demercuration of alkynes? It's mercuration, so it's maybe mercury, HgSO4, H2SO4. It's either, people either write HgSO4 and H2SO4, or HgSO4, H3O plus, H3O, acid water, right? I'm not going to review the mechanism because it was really chapter 13 stuff, alkynes. It did go through something called a Mercuronium Complex. That was the weird kind of like 3-member ring with a mercury, if you remember that. It looks kind of like, I'll just abbreviate it. I kind of drew it this way, plus charge with the X group on it, and then essentially that was electrophilic, acts like a secondary carbocation. So water would attack that side, which is where the oxygen came from, open it up, and then the mercury gets lost. Okay, that's all chapter 13. Okay. The book mentions one more method. I'll mention it very briefly. It's called allylic oxidation. Allylic oxidation. Manganese oxide, MnO2, selectively oxidizes allylic alcohols. What is allylic alcohol? Allylic. Remember that word? You may have heard it at some point. Allylic just means next to a alkene. So next to alkene. And we can selectively oxidize an allylic alcohol using MnO2. And I'm just going to show an example. No mechanism. Book mentions this, that's why I just want to bring it up. Steroid. OH, methyl, OH, methyl, alkene, OH. So now you see the allylic alcohol. That's the allylic alcohol. We have two non-allylic alcohols and one allylic alcohol. And we do MnO2. So what's the product going to look like? Let's draw the skeleton first. The non-allylic alcohols don't get touched, while the allylic alcohol gets, what happens to the allylic alcohol? What do we say? It gets oxidized. So this alcohol gets converted to a ketone. Okay, kind of cool. It shows some what we call selective chemistry, where we can selectively operate in one functional group and not other functional groups. Probably what happens is something about the manganese coordinating to the alkene, and then it causes the oxidation. But no mechanism. It's a cool reaction. A million uses in organic chemistry, so that's kind of cool. Cool. Alright, so now, new stuff. Reactivity of carbonyls is new, for the most part. You've seen some of this, but general reactivity of carbonyls. Overall, if you think about a carbonyl like a ketone or aldehyde, what are the things that could possibly happen? Like, we know that this is delta minus and this is delta plus, right? One of the things you know is that nucleophiles attack ketone or aldehyde, right? You learned a little bit of that, Grignards and stuff. And this is going to be kind of chapter 17, so our current chapter. The other thing is that the oxygen can sort of attack electrophiles, because it's got a lone pair and kind of nucleophilic. So this is also chapter 17. We also got a proton next door, right? And you can almost imagine, because the proton is somewhat acidic, is that base can take the proton and sort of like kick the electrons towards the ketone or aldehyde, and then do reactivity. Like, indeed, it can actually, you can almost like take the proton off and then they can go attack electrophiles. This is chapter 18. This will be the next chapter. So you have 17, we have 17. So for the most part, this chapter is all about stuff attacking the carbonyl and also like the oxygen attacking other stuff. Alright, and just as a preview, you know, another thing from chapter 18, the next chapter, is that if you have a ketone, it can tautomerize to the enol. So we'll start learning about enols here pretty soon. Enol keto. and the enol can actually go attack stuff, electrophiles. So the enol is actually nucleophilic. Enol can attack stuff. So this is all chapter 18 also. So you can see that chapter 17 and 18 are kind of complementary. 17 is kind of like stuff attacking the ketone or aldehyde and maybe the oxygen being a nucleophile, whereas 18 will be stuff related to the next door position. Okay. There's, I think, tables 17.3 and 17.4 are a summary of the different kinds of reactions. So you can take a look at that as we go through them all. Alright, so for me summarizing it right now, the main types of reactivity for this chapter are going to be what I call basic addition. By basic I mean like a base, some kind of base type, basic nucleophile we'll say. So if we have a C double bond O, and it can be reversible or irreversible, but we got a nuke, some kind of nucleophile, basic conditions. So basic conditions, not acidic. By basic I mean non-acidic, right? The idea is that the nucleophile can just attack, because this is delta minus, this is delta plus, right? So yeah, the nucleophile can attack. That's kind of what a Grignard does, for example, irreversibly. Then you got O minus nuke, and then maybe water or some proton source will donate a proton. And what do you get? Alcohol. Okay, this is roughly what a Grignard does, right? Grignard attacks, and then you get a proton. But now we're also going to do acidic addition. Acidic addition, and the mechanism is going to be a little different. So if I have a ketone, there's also delta minus, delta plus, right? For a acidic style addition, delta minus, delta plus, the idea is that we'll have H plus that's acidic, right? And a nucleophile. Okay? And it's going to be different. It's not like the nucleophile is just going to attack. The first step is actually the oxygen grabs the proton. Okay? And what does that give you? A protonated ketone or aldehyde, right? Alright, does that have any resonance? Is this a happy non-resonant structure, or does it have some resonance? And the answer is that it totally has resonance. Okay, I can push the electrons up onto the oxygen, and now what is it? C double bond O, C single bond O, and then OH. Where's the plus charge now? Where did the plus charge go? If the bond went up, you need a plus charge somewhere, and it's down at the carbon, right? And I call this an RSCC, which we've seen before. Resonance stabilized carbocation. Resonance stabilized carbocation. Okay? And then, what's the nucleophile going to do to that? What's the nucleophile going to do to that plus charge? Kind of attack from the top there onto the carbon, right? So not to the bond, but to the carbon, right? I should maybe be more clear. To be nice and clear, let's redraw the plus charge being right here, maybe, and the arrow going to the carbon. And now the nucleophile is attached, and you get an alcohol. Okay. And it kind of looks like the same sort of product as the top. Okay? Alright. Yeah, the nucleophile is now attached, and you have an alcohol. Alright. Okay, so our first example of this is really easy. We start with the easy, then we move to the complicated. So addition of water to a ketone or aldehyde to form something called a hydrate. So a hydrate is just the addition product of water. Okay, let's show a simple example of this. And it's all related to the idea of water attacking a ketone or aldehyde. So let's show acetone, OH2, water. And first of all, there is an equilibrium. This is all equilibrium. We're going to have a lot of equilibrium in this chapter. And when water attacks the ketone, you get OH, OH. Okay. And this requires a catalyst, either acid or base. So H plus or OH minus catalytic. Okay. So there's a little bit of acid or a little bit of base, but it causes this reaction. It's not tremendously favored, so the equilibrium is kind of on the left favored and not too much on the right. And this is called, the product name, what do you think it's called? This is acetone. What do you think this is? Hydrate? It's called acetone hydrate. Right? And the equilibrium is not very favored, so this is roughly 99.9%, so really it wants to be on the left, and this is about 0.1%. So that's, like, why is this even interesting? Well, the mechanism is interesting, and also for other molecules, it's more favored, right? Acetone just happens to be kind of low favored. Why do you think it's disfavored? Is there anything kind of unhappy about this molecule? Yeah, the main reason is sterics, due to sterics, right? You got a lot of congestion. Everything's kind of bumping into each other. Like that's bumping into that, that's bumping, a lot of bumping interactions, and that's a steric clashing, and that's why it's not very favored. But if you get rid of the steric clashing, this actually does happen, and we'll see that for aldehydes. So, example for formaldehyde, which has some similarity to acetone. Do the same exact thing, water, and it actually goes all the way to the right, and you get that. This stuff is called what? It's formaldehyde. This stuff is called something hydrate, like formaldehyde hydrate. And this is 99.99%. So it's very favored, and this is like 0.01%. So formaldehyde really loves to be in the hydrated form. Okay? What do you think we need? A little bit of acid or base to catalyze this. So you need a little bit of acid or base for catalysis. Okay? Cool. And of course, do you think there's any steric crowding here that makes it unhappy? Well, not really. Obviously, the equilibrium being far to the right favored makes it seem like it's not sterically hindered. So no steric crowding. And that's why it's so happy. Okay. You know, why do you think it's also happy? The reason this reaction kind of goes is we're trading a sigma bond and a pi bond, because there's a sigma bond and a pi bond, right? Here we have two sigma bonds, and the sigma bonds are actually more happy because they're stronger bonds, I guess. So thermodynamically, if we're thinking about like the stability of this, why does it happen? Because we're trading one sigma and one pi bond, right? That's the double bond. We're trading a sigma bond and a pi bond for two sigma bonds. And those are stronger. So that explains kind of why, you know, why the bond strengths make this a happier molecule. Okay. All right, so let's see. In the mechanism, we'll do the mechanism next. It's either acid or base catalyzed. So we'll show both mechanisms, and those are going to be a guide for almost all the mechanisms in this chapter, these acid and base catalyzed ones. So you need a little bit of acid or you need a little bit of base for it to go. If you don't have those, so if we say neutral pH, at neutral pH, which basically means no acid, no base, it's very slow. Reaction is slow. Because you need the catalyst, right? And the catalyst is caused by either acid or base. So now let's do mechanisms of these reactions. They're really easy. We'll do acid, catalyzed, hydration. So this is for ketones or aldehydes. The mechanism's all the same. We'll show it for acetone. Now even though the mechanism is disfavored, it wants to stay on the left. The mechanism is all the same, though. No, we don't care about thermodynamics right now. We're just going to go through the mechanism of like how we get from here to there. Okay. So we're reacting with water and acid. Sometimes we just say H3O+, right? Okay, so what did we say earlier about the mechanism of how we might get a nucleophilic attack through acid catalyzed process? Because we did this already 10 minutes ago. What's the first thing? Oxygen grabs the proton, right? And that makes an equilibrium. And what's this thing? 4 letters. We gave it a name, acronym. RSCC, right? Where's the plus charge now? It's right there. RSCC, resonance stabilized carbocation. And these are always electrophilic. They like to be attacked. Okay, so we got some water around. What do you think water is going to do to the RSCC? This is an electrophile, this is a nucleophile. I'm just going to maybe sneak around and attack there. I always want to go straight to the carbon. Alright, so now the water gets attached. And any guesses what the last step is? These are all equilibrium, right? we have oxygen with 2 protons, we have oxygen with 1 proton, so maybe somebody takes off that proton. So maybe more water, right? You got water around. Okay, that was pretty doable. I hope you agree. Acid catalyzed hydration is pretty straightforward. Alright. Okay, also the, you know, what's catalytic here? The proton's catalytic. It's acid catalyzed, right? The water is not catalytic. It's actually consumed in the process of the reaction. Okay? Alright. But the acid is definitely catalytic. Okay, cool. What about the base catalyzed mechanism? How would a base accomplish the same reaction as the acid? It's very simple. Okay? So for the base catalyzed reaction, you got some base, you got some water, you get the same hydrate. Alright? So this is actually even easier. And remember what we talked about earlier, how acids do one thing, bases do another? And with bases, you just have direct nucleophilic attack. So if I have hydroxide, I don't have to activate the oxygen like protonate it, the way we protonated above, right? We don't have to do that because we actually have a good nucleophile already as a base. It just attacks. Alright, that makes it easier, right? Where are we trying to get to, right? One hydroxy is attached. Yep, and now we have O minus. And what do you think we need to do lastly to finish this off? Is just grab a proton from water. H2O. Cool, so this is pretty easy reaction mechanisms. And this is a good preview for the entire chapter. We have a lot of these kind of acid catalyzed reactions where you protonate, make an RSCC, nucleophile attacks. Then we have some basic ones where usually with the basic ones the nucleophile just attacks and then you do something else and then you get your product, alright? Okay, one more thing about the hydration real quick is that some, like we talked about how some things are easier or work better than others. We have relative rates of hydration for some molecules. It's the speed of the reaction. And there's a couple things that are really, really fast. That, like, this aldehyde is, I forget, trichloroacetaldehyde is super, super fast relative to like formaldehyde, which actually also is super fast, but it's not as fast as that trichloro stuff. And then we have like acetaldehyde and then acetone, which we've already talked about how there's some steric hindrance with ketones, you know, ketone versus a normal aldehyde versus formaldehyde, and then this stuff is just like off the charts in terms of very favored for hydration. The reason this is so favored is the trichloromethyl are, you know, they're all delta negative, and they're kind of stable. They're pulling electron density from the aldehyde, so the electron withdrawing group, and there's like 3 of them, increases the carbocation character of the carbonyl. And that's kind of why this is just very, very reactive. And then here we talked about the hinders, highly sterically hindered ketone, and that's why it's like not as fast. Okay. Okay, so that was it for the hydration. Let's start this topic, and we'll probably end on it today, which is very similar to hydration. It's the addition of alcohols to ketones and aldehydes. Alcohols. So it's a little different than hydration, but there's similarities. When you add an alcohol to an aldehyde or ketone, you form first something called a hemiacetal, and then it continues usually to form an acetal. So I'll explain what those two things are. It's basically, they're the alcohol addition products. So alcohols, we know alcohols, they add to ketones and aldehydes, kind of to make a hemiacetal and an acetal. What are those two things? Okay, so I'll show a quick overview of what we're talking about here. So if we have a ketone, and we, so it's or an aldehyde, it could be ketone or an aldehyde, and let's react to this with an alcohol, HOR, and we can react this with either acid or base catalysis. Okay, pretty cool so far? It's going to do the same exact thing that a water did when it reacted. Now, the first, after one alcohol gets incorporated, you get OH and OR, like the alcohol is attached. And this is what we call hemiacetal. Hemiacetal. Alright? Now, if you are under acid conditions, so H plus cat only, so assuming you have acid around, it'll keep going. And then you have two ORs. Does that make sense? We'll explain why it does that. And this is what's called an acetal. Okay, so we go from, the hemiacetal is kind of like a middle point of reactivity. It goes from the ketone or aldehyde to the hemiacetal. And if you're using acid catalysis, it'll keep going to the acetal from the hemiacetal. But if you're using base, the furthest it can get is to the hemiacetal. Alright? Cool. So I'll just show one quick example of this. So there's kind of like two situations, and I'm just going to show one quick one just so we can end on a real example. Okay, and the first one, we'll continue the next lecture with the next one, is intramolecular hemiacetal formation. Intramolecular, which means within the same molecule, hemiacetal formation. So just as a quick closing example, aldehyde, I'm going to have like alcohol, like that. Alright. When you have a molecule like this, we're going to react it with either acid or base. This will always only go to the hemiacetal, which is something like this, like a closed system. So it's like 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. The example, and this is this an acetal or a hemiacetal? This is a hemiacetal, right? Because you only have one OH and one like carbon-oxygen, carbon type bond. Okay. The mechanism is incredibly easy, and then we'll stop. All right. So what do you think? We're just gonna do the acid one here. What was the first step of the acid catalyzed reactions that we learned about? You protonate the carbonyl, right? And that makes an RSCC. Okay. Now, I'm not going to draw both resonance structures of this. You could if you want, but this is an RSCC, right? RSCC. And we're very close to the product. All we have to do is just have this guy attack. Okay? It's basically the product now, OH. And what do we have to do? Take off the proton with like water or something. And that is all there is to it. That's your first example of a alcohol reacting with a aldehyde or ketone to make like a hemiacetal. Next time we're going to continue with the other variations, not intramolecular but intermolecular, where the alcohol is kind of disconnected. But the book starts with this example. So this is where we'll start, and then we'll go to the kind of more interesting examples next time. All right. So the two situations means intramolecular, and the second situation will be the intermolecular, which is like between two, like the alcohol will be disconnected and then become connected. Okay.